I'm Rossella Splendido. I'm the team lead of the network team in SUSE that takes care of NFV, SDN, and networking in general. So today I will explain so very broadly, some of the most common buzzwords in networking nowadays, like SDN and NFV. Then I will explain a little bit how networking in OpenStack works, briefly how networking for container works. So it's going to be a lot of stuff, but so I will try to not to dive too much into details, just to give you an overview, but feel free to interrupt me anytime if you have any question. So I guess a good starting point is traditional networking. Probably most of you in the room are familiar with with network devices, cables. So that's the way we used to do networking. We still do that because we still need the physical networks. But now there's more complexity because the virtual world came in. And as you can see here, it's not that traditional networking was easy. You can see from this map, there are already lots of protocols that you need to know. And so in the virtual world, you need to know all this, and on top of that, also how the virtual networking actually works. So let's try to understand why actually we needed virtual networking. So which are the motivations that led to the creation of this new concept? Thing is that traditional networking has its own limitation that we wanted to overcome. First of all, so most of the limitation came from the fact that traditional networking is hardware-centric. So the focus is on these devices. They are physical. You cannot move them very easily. They don't scale so much. You need people to physically go there and plug stuff. So let's now go more into details into these limitations so that then we can understand better how visual networking works and why it was needed. So as I was saying, these hardware devices, they are usually a closed system because, hardware vendors, their job was to produce the best devices in the world. And the idea was to use closed software so that you could use that only on those devices. Those devices are expensive because, all the intelligence is there. And they are also hard to interoperate. Because if you buy from one vendor, it's not so automatically that it will support devices from other vendors. And so, and they are also expensive. So this is not so good if you want to experiment, innovate, and so on. Then another thing is that it's not scalable. Like if you want to scale up or down, this summarized in adding more devices or removing those devices. And also you need to do the piping again. You need to send somebody to configure the network. So it's kind of, heavy work. And probably, at least for me, the most important part is that there's no abstraction. So you just, you stick to the physical world, and that's what you have. It's hard to think of, models of like networks, virtual network, that doesn't exist. Everything is physical, and it's configured on the devices. And in this doesn't help with the innovation. And also, it's kind of hard to experiment because if you want to experiment something, you need to buy the devices, you need to wait till they arrive, then you need to plug them, and it's just it's a long process. And also another point is that those devices are hard to maintain. So they are physically located somewhere. If you need to configure them differently, most of the times you need somebody on site that does the plumbing or configure the switches. So it's it's hard. And then another drive for innovation was the beginning of server visualization. So when you start having VMs on servers, then of course you need a smart way to connect those VMs. And at the beginning, the easy answer was to use VLANs, which is still a good way to do that, but yet it has a limitation. It's not so flexible. So if you start having lots of VMs on different hosts, and that doesn't scale very well. And here it's a very simple example of how we used to do things maybe 20 years ago. So when somebody needed a new machine, you need a technician that physically goes there, reach the office, the whatever, the place where you want to connect your machine. And of course, then you need to physically plug the cable. And then you need to configure the networking to handle this new machine. And we will see later how that works in the virtual world. So all the limitations that I was describing before, they led to the idea of having a new way to manage these physical switches, network devices in general. And this led to the creation of OpenFlow. I don't know how many in the room are familiar with the word OpenFlow. Yeah, you are. Anyway, OpenFlow, as the name says, it's open. It's an open standard. And the main idea behind OpenFlow is to separate the control plane from the data plane. And the data plane is the packet processing, the fast packet processing that doesn't require any routing decision. The control plane instead is, say, the intelligent part, the one that makes the routing decision. So if you divide these two aspects, then you can easily handle the data plane using flows. This is a new concept in OpenFlow. A flow is composed by two parts, a match and an action. A match is specific part of fields in the packet that you want to match with a specific value. And the action is the action that you want to execute when you match this packet. Like, for example, a very stupid one, I want to drop any TCP packet. So the match would be TCP, and the action would be drop. And if I install this flow on the OpenFlow switch, what it will do, it will just match every TCP packet, and it will drop it. So what happens when this OpenFlow switch receives a packet that doesn't match any flow that it's installed? It will just go to the controller, because the controller is the component in charge of the control plane. So it's the intelligent part that makes the routing decision. And of course, the controller is also in charge of programming this OpenFlow switch. And a switch, the way you program this switch is basically to install flows into its flow table. And I just want you, I will explain very briefly, because this thing, if you want the details, they are very interesting, but I will try to give you just an idea of how an OpenFlow switch works. So we have tables of flows. They have numbers, and of course you go from 0 to n. When a packet comes in, the first thing the switch does is try to see if it matches any flows that is installed. And then, so you can also have a special kind of action for a flow that basically sends the packet to another table. Like I could install in table 0 an action to say, okay, check table 3, for example. And then the packet would check, so the switch would check if on table 3 there's a match for this packet, and go on the processing. So to process a packet, you could go through multiple tables, and this processing ends when you reach an action. That could be, packet out of port 3, or could be drop, or anything. So not anything, but an action. And this is how an OpenFlow switch works. Yeah?
This is all happening on the control plane? Or is it
No, on the...
No,
this is happening on the OpenFlow switch. It's very fast, even, it's optimized for that. On the control plane, only the routing decision happens. Like when you get a packet, it doesn't match any flow, so you need to decide how to route it. Okay, and so OpenFlow paved the way for SDN. So now let's, because SDN, I guess it's a term used a lot in the last days and sometimes abused. So what's the idea? You know, it's software-defined networks. But what does it mean exactly? So it's, the idea is very similar to what I described for the OpenFlow standard. Again, is to just separate the control plane and the data plane. Why? Because in the data plane, you can just do fast processing, and in the control plane, you can put all the intelligence there to route packets in a smart way. So just dividing those two things, you can really centralize the control, and you can develop what we call SDN controllers. And you get to a point where instead of configuring a network, that it's what we were doing in traditional networking, you can just program a network. And so you can see here, I have a clicker, I think, okay. You can see here how this, a small diagram. Here you have your business logic, your application layer. Here you have the control layer, and here you find the SDN controller. And then this SDN controller can use, uses protocols to talk with the infrastructure. So it could use OpenFlow, which is also a protocol to configure the switches. It could use other protocols like netconf. There are others. And in this way, this intelligent layer can configure the infrastructure. So that's the main idea behind SDN.
What are the network services?
Network services, sorry? Yeah. Here, it can be anything. It can be a firewall, load balancer, netting, whatever you like. I mean, it's... Okay. So another concept that it's part of SDN is overlay network. I think this picture really describes more than 1,000 words what it is. The thing, you have a physical network. That's what you always have. And then the concept of overlay network is you create a virtual network on top of this physical network. So of course, this virtual level is an abstraction. So the packets will still flow in the physical network. But there's this overlay. There's this physical network. It's just an abstraction, and it's managed by the SDN controller. And of course, so the state is restricted at the edge of the network, because there's where you take the routing decisions.
When you say it's managed by SDN,
Yeah, that's a very good question. It takes a very long answer, and it depends a lot on which SDN controller you use. So a very simple case would be you can create an overlay using tunneling. So basically, you have one compute host where your VMs are, and then you have an SDN controller, something intelligent that takes care of the packets. And so this SDN controller will just take care of installing the proper routes to route the packets coming from a VM to where it needs to go. And if it needs to go on another host, it will just tunnel the packet using some encapsulation technology like VXLAN or GRI.
So is each one of those a virtual network?
Yeah, this is just like a simplified picture, just to show that, you know, here you have the physical devices, and here you have virtual devices that could be virtual switches. It's really just.
The environment to support multi-tenant.
Yeah, you can support multi-tenancy. I mean, it depends on how you handle the networking. So multi-tenancy just means that you need to isolate the traffic. So it just depends on, you know, which SDN controller you use and the way that it enforces this isolation. A very simple way, for example, is to use VLANs to isolate the traffic. Okay, so going back to my example, so in the virtual world, all you need to create a new machine, it's basically a click. you see here the dashboard of SUSE OpenStack Cloud, and really that's all you need to get your machine up and running and connect it to your network. So even with this simple example, you can see how things got faster and easier with the virtual world, even if maybe they are a bit harder to understand for us technical people, that we need to know the details. So, okay, so now let's move to another very popular word, NFV. It's network function virtualization, and I've heard you know, many people describing it in many ways, but for me, really, the easiest way to understand this concept is that, you know, this as an NFV was created by telcos companies. Their focus was to, you know, spare money, be more flexible, and so what's behind this network function virtualization? The idea is simple. They spend lots of money for advanced network devices like the one you can see here, and what they want to do is, instead of using these physical devices, they want to virtualize everything and use commodity hardware. So that's really the simplest way of describing it. And why? Again, it's the benefits are the same, more or less the same that I was describing before. In this way, you are more agile because, of course, you know, you don't need to buy stuff. You could just, you know, have whatever hardware, and you can reconfigure it very easily. You have reduced costs, of course, because these appliances, they are very expensive. You have faster time to market because, again, you don't need somebody that physically climbs on a to install all your physical devices. And you have interoperability because if everything is virtual, it's easier to enforce interoperability instead of having 1,000 of physical devices that are produced by different vendors. And so let's move to OPNFV. OPNFV, it's an open source project whose goal is to deploy and test NFV solution. SUSE is a part of OPNFV, and I just want to describe very briefly the architecture that you see here. So in NFV, the goal is to virtualize network function. A network function is really could be anything, like could be a firewall, could be DHCP, is anything that in the traditional networking, so it's some traditional networking concept that it's translated into the virtual world. And so you can see, it's not probably very clear, but here you have, on the top level, you have orchestration and management. So this level is the level where the network functions are configured and managed. Then, of course, this network function, they need to live in some architecture. So there's the NFV infrastructure, that it's this gray area. And in the OPNFV, they decided to use OpenStack for the NFV infrastructure. And to use as SDN controller, they use OpenDaylight, ONOS, and OpenContrail. They are as open source SDN controllers. So that's the reference architecture. And for
So those are two competing SDN controllers, or do
yeah.
they work together? Or?
No, they can work together, but they are different projects, yeah. And so what OPNFV also offers is a way of to do continuous integration, so that they have these labs where they test all the solutions. And yeah, that's it. Now I just wanted to give you a bit of insight in networking, how networking works in OpenStack. Since, as I was saying before, OpenStack is used also for NFV, and of course, OpenStack is also an SDN solution somehow, or better, uses some SDN solution. So the project in OpenStack that takes care of networking is Neutron. You probably heard the name, I hope. And really, the goal of Neutron is to provide networking as a service. So just to manage the connectivity between these virtual interfaces that are connecting to VMs. And it also provides an API to be able to configure this connectivity. So in the most important part is this API, because Neutron, we will see later, is extremely pluggable. So you can use plugins to configure SDN controller to manage the network with Neutron. So really the part that stays is the API. It's a standard API that you can use to configure the networking. Yeah?
If you have an SDN controller already working, one of those two that you mentioned, what exactly does then Neutron add to that? What does it do on top of those SDN
Okay.
controllers?
It's a good question. So that's why I was saying it provides an API, and that's the most important part. Because what Neutron does when you have an SDN controller configured, so all the networks are managed by the SDN controller, which is kind of plugged into Neutron. So what Neutron does, it just exposes this API that it's used then by other OpenStack projects. So it's basically just a central point, and then it passes the information to the SDN controllers. And yeah, another point, what does Neutron do? Also, Neutron defines the abstraction that are used by OpenStack for virtual networking. I put just some of them. You know, they are very similar to the physical concept. Like there's a network that it's an L2 broadcast domain. There's a subnet that in Neutron is actually a bit different, because a subnet is just a block of V4 or V6 IPs. So you could also have a network with different kind of subnets. And then, of course, there's a port that is the interconnection point for devices. Then you have a router. You have much more. You have load balancer. You have firewalls. And yeah, but I would say almost every concept in the physical world is mapped into the virtual one. And one of the strong points of Neutron is that it's pluggable, it's modular. So on the back end, you can use lots of different technologies, because there's this concept of plugins. So you use to use Neutron, you have to define a plugin, and this plugin will actually then take care of doing the real plumbing. So the vanilla Neutron uses OpenVSwitch or Linux Bridge, but again, you can configure plugin for SDN controllers, even for some Cisco switches. So there's a variety of technology that you can use.
Yeah. Can those APIs enable that cloud infrastructure or Neutron to be able to control external devices if they interface with the API?
They don't interface with the API. There's then always some kind of controller that configures the physical switches. No, thank you. And so one important process is the Neutron server, that it's the one that exposes the API. Now let's see how a typical OpenStack deployment looks like. I will focus only on the networking part. So you have a controller node. In the controller node is where the Neutron server is running, so where the API is exposed. Then you have a network node. And in this, as the name says, this is the node specific for networking. So what does it mean? In this node, you have the Neutron agents running. And this node is also connected to the external network, so to expose the cloud to the external world. So let's describe a bit. Neutron has a few agents. Let's describe a bit what they do. So on the network node, we have the L3 agent running. The L3 agent is the agent in charge of L3 connectivity. That means that it's the agent that creates the routers. And a router in Neutron is a network namespace. And also, the L3 agent is the one that manages the connectivity to the external world, so the connectivity to the public network. Then we have the DHCP agent, that is the agent in charge of managing DHCP. We have the metadata agent. So metadata are data that are needed by the VM, and these are stored. Stored somewhere by Nova. So this metadata agent in Neutron is just there to retrieve this metadata for the VM and to provide them to the VM. Then we have the L2 agent. The L2 agent is the agent in charge of L2 connectivity, and this agent runs on every compute node. A compute node is a node where Nova Compute runs, so where the VMs are actually running. So the L2 agent responsibility is to set up the networking on the compute node so that the VMs have connectivity.
So the L3 agent, you said that runs inside the network node.
Yeah.
Not a virtual network node.
The network node is not virtual. It's a physical node. So all these nodes are physical. Network, compute, and controller, they are physical hosts. On these physical hosts, we have software running. We have OpenStack running so that we have this, the cloud, the virtual. Okay. Yeah?
Does the L3 agent provide the natting capability
Yeah.
then?
Yeah.
That allows the...
Yeah, correct. Okay, so I also wanted to show what we call advanced services in Neutron. We have this project that they were created a bit after Neutron, and they have their own, like, they are separate projects, but they just enhance some functionality in Neutron. So we have here the load balancer as a service. In the load balancer as a service, as you might imagine, you just want to have a load balancer. To do that, you define a pool. A pool is just a group of machines. And then you associate a virtual IP with the pool. A virtual IP is the IP that you will use to reach the service, the IP that is then load balanced. And then you have the listeners that are, that it's a configuration of these virtual IPs. And then you have the health monitors that are monitors that just make sure that the load balancer and the pool is still healthy and up and running. Oops, sorry. So in this example, I have a load balancer with a virtual IP of 20006. So and of course it's connected to a router. So when a packet arrives that it's meant to go to 20006, the load balancer will handle it, and it will, according to some policy that you configure, like round robin or any that you like, it will just then forward the traffic either to VM1 or to VM2 that are VM1 and VM. Oh, okay, this doesn't work anymore. Okay, VM1 and VM2, they are part of the same pool, and they are associated with the same virtual IP.
So that load balancer is part of Neutron?
Yeah, Yeah. Well, there's always this question, what's NFV exactly? Yeah, but a load balancer is also part of, the NFV world, yes. Then we have VPN as a service. This is another project that allows you to connect to a remote site using VPN. And under the hood, it uses IPsec or OpenStack. And so I think the picture is self-explanatory. You just have two different sites that are connecting using this VPN.
Is that, can I just ask, is that in SUSE Cloud 6?
I think it's in, no.
We, right now, I don't know which project was already deprecated.
Yeah, it was deprecated, but then now they are reviving it.
Yeah, probably we have the packages, but they are not installed automatically. So if you want to have this feature, you have to install the package and configure it by your own. As I'm assuming we have package already.
The 7?
Yeah.
Yeah.
In Cloud 6 as well.
Great, thanks, Micha. So we have another one that it's a firewall as a service. And the idea here is to have an enhanced router that can also act as a firewall. So for example, here you have 2 VMs, and of course, all the traffic that needs to go to this VM, it will be filtered by this firewall that you can configure. And yeah, it's you can block some kind of traffic or not. Okay, now let's move to containers, which is very new. Yep.
Really quick. So, how many NFV functions have actually been virtualized, and how many are still remaining that are maybe infancy projects that can be utilized by OpenStack? Is there a list of NFV functions?
No, I would love to have a list. So in OpenStack, we have the project that I described, the firewall, load balancer, and VPN. We also have BGP, VPN. We have other projects, but there's not a specific list, complete list of virtual network functions. So every company might come up with yet another, and also the NFV solution. There are several NFV solutions, and most of them are proprietary. So we don't have insight on what they do. So yeah, but in OpenStack, I would say, apart from what I said, there's another project. It's for service function chaining. There's a lot of things, but it's not a complete list. Yeah.
About load balancer and VPN. What did you say about firewall? That would also be a good NFV function, right?
Yes. No, we are because so this firewall is backed by a project that is called Firewall as a Service, and so in the OpenStack community, in the last few years, nobody really contributed to that project, so they decided to deprecate it. Yeah. But then, now it's more contributor just came up, and so they are reviving it. Yep. So a few words about networking for containers. This is a very broad topic. That's why I decided to talk only about one project, that it's Courier. Okay. So containers are very cool. I guess probably everybody in the audience is familiar with what containers are. But of course, they put some challenges in terms of networking. You have multiple containers in one host, and you want to be able to connect them. And then things get even more complicated when you have several hosts, and you want to connect the container on several hosts. Then you might want to enforce some ACLs. So that it's really a challenge. Then you can have an host, a VM, and inside the VM you can have containers. So that there are really lots of level of abstraction here. That's why the Courier project was created to integrate networking for container into OpenStack. It's part of the Neutron Stadium. The Neutron Stadium is just a definition for projects that are affiliated to Neutron. It means that they follow some practices and that they release according to the schedule that we use in OpenStack. And the main idea is, again, I really stress the API. So the main idea of Courier is to be able to control the networking for containers using the same Neutron API. Before Courier existed, people were already developing side APIs to be able to handle container, and this project really brought container and VMs together under the same Neutron API. So here, just show briefly, so Courier, what it does, it maps the abstraction of lib network that it's meant to handle the networking for container. It just maps this API into the Neutron API. So it's a pass-through so that we are able to configure the container networking using the same Neutron API. And another very important thing is that with Courier, you don't lose all the networking services that are provided by Neutron. So you could also use a load balancer, firewall, and all the stuff that we already have in Neutron. You can use it in the virtual world. And that was my last slide. Yeah, questions?
Can you explain how Neutron creates virtual networks and how that works with OpenStack?
Yes, it's you have to have lots of fantasy because I don't have any graph now, but I can explain. So you have a compute node, okay? On this compute node, with the Open Daylight integration, with the most simplest one, you use Open Daylight with OVSDB. So with Open vSwitch. So in the compute node where the VM with the VMs are running, you have also Open vSwitch running. Open vSwitch is composed by the Open vSwitch agent and the OVSDB. The OVSDB is the database where you store all the network configuration, basically. So when you create a VM, it's a long story, but at some point Nova will notify Neutron to set up the networking. And at that point, Neutron, since Neutron uses plugins, it will if you configure Neutron to use Open Daylight, then this network creation will be notified to the Open Daylight controller. The Open Daylight controller, of course, will control Open vSwitch on that host because that's how Open Daylight works. And it will just modify the OVSDB, so it will just issue a call to add something in the OVSDB to create the networking for this VM, and then the OVS agent will pick that up and will create the port and everything else.
That was excellent.
Yeah,
it's hard without drawing, but.
So for virtual networks, you have like encapsulation of the virtual network IP address with the physical layer IP address. Is that how it works?
So that's how it works. If you have two compute nodes and you have one VM on one compute node and the other VM on the other compute node, even if they are on the same virtual network, physically they are on different hosts. So you need a way to connect these hosts. And in that case, you use encapsulation. So on this compute node one, in this case, the OVS agent will just notice that the VM you are trying to reach is not on the same host. So it will just know that it's on, say, host B, and we know that the IP, so the tunnel endpoint of host B, because there's another think that, you know, when every host comes up, they just advertise the tunnel IP, so this information is stored into a database. That's why the agent knows where it is, so it will just encapsulate the packet using you can use VXLAN or GRI, and the tunnel endpoint will be the IP of host B. Then the packet will reach host B, it will be decapsulated, and then of course we'll see the IP of the VM, and on that host it will be routed to the VM.
So how about other projects? We are going to ship only open daylight, or we are still looking on the VM?
Yeah, we are exploring, we are looking, but I don't know what we will ship in the end.
Can you repeat the question?
Oh yes, he was asking me, you know, how about other SDN controllers or other SDN solution like OVN, and we have OpenControl, ONOS, and you know, Midonet, and so on.
Yeah, we used to work on different projects.
Yeah, so right now we are exploring, but we still haven't decided what we will ship in the end. So.
But we are sure that Courier will be secure.
We are not sure. I just wanted to talk about Courier because I had another talk yesterday about networking for containers, and I didn't mention Courier, and so yes.
So there are open source controllers, but there's also, you know, proprietary controllers.
Yes.
So then it becomes a discussion of which ones do we SUSE with our OpenStack want to support. Is that kind of what that question was about?
Yeah, but actually we are looking only at open source controller now. I mean, apart from this.
NSX.
Yeah, NSX, yeah.
Is OpFlex, so Cisco OpFlex, is that a Cisco's controller?
I think OpFlex is a protocol that they use to configure the switches, but I might be wrong. Anyway, yeah, you know that we will look into that, so yes.
A question about the way the SDN controller about Open Daylight, you said it works with Open vSwitch. So what function does Open vSwitch do for Open Daylight? So Open Daylight is the SDN controller, right?
Yes.
And then Open vSwitch is what in that context?
Yes. So again, with a lot of imagination, a few words about Open Daylight. In Open Daylight, you have a concept of northbound API and southbound API. So in the case of the OpenStack integration, the northbound API will be Neutron. The northbound API is the API that the user might use to configure the stuff. The southbound API is the API that is used to talk to the fabric switches. Okay, so with Open Daylight, you can also integrate Open Daylight with with several solutions. For the OpenStack integration, they picked the easiest one, that is Open vSwitch. But you can also configure Open Daylight to talk directly, I don't know, to Cisco switches or to other switches.
So if you use Open vSwitch, does it is Open vSwitch able to talk to different types of physical switches? Or
No. Yeah. Okay, no, there's, from a technology point of view, there's no value added. It was an easy solution. The value added is that you can integrate Open Daylight with other controllers. So you must, not other controllers, other solutions. Like, so you might have Open vSwitch, and then you might have, other physical switches. And Open Daylight uses OpenFlow to control the switches. So you might use OpenFlow also to configure directly the fabric switches. But in the OpenStack integration, they use OpenFlow to configure the Open vSwitch that is running on the compute host. Of course, you can replace it with a physical switch.
At the end of the day, these tables that you were talking about have to end up on the physical.
No, it's on the table. Yeah, it's on the compute.
The table is on the computer, right? So
Yeah.
This table, is it part of the layer 2?
No, this No. This table is the flow table that is used by the OpenFlow switch. So in this case, the OpenFlow switch is OpenV switch, but also any other OpenFlow switch will have a flow table. Even physical switches that support OpenFlow, they just store this.
OpenV switch is not a fabric switch, right?
No, it's virtual. Yeah,
it's virtual, right?
Yeah.
So how does it, at the end of the day, the fabric switch needs to know what it has to do? Is the OpenV switch telling it what to do? Or at the end of the day, the packet transfer is happening on a fabric node, right? It's not happening. Everything else is an abstraction, isn't it?
Yes.
Right?
Yes.
So if OpenV switch has these flow tables, at the end of the day, this information has to get down to the fabric switch somehow. Right.
Yes. So the way it works is what I was explaining a bit before with the encapsulation. So the OpenV switch on the compute host manages the connectivity inside the host. So these flows are basically used to know that when VM1 wants to talk with VM5, you just the packet needs to go to some specific port on the virtual switch. Okay, and also OpenV switch has the flows to handle the tunneling. So when we have a tunneling, it's also a flow in the switch. So when you want to reach a VM on another host, it will just encapsulate it, and then it will run, of course, on the physical network, but it's encapsulated.
So that means that if I have my VMs all on one compute node, basically, then OpenV switch obviously doesn't have to talk to any fabric switch.
But no, so it doesn't talk to any fabric switch. It never does. The underlying networking, so you have to configure it. The only thing that is required, of course, is that you have connectivity between the compute hosts. Then, yeah, it doesn't really need to configure the physical switches. What you are asking, so you can use OpenDaylight with the physical switches. In this case, so if you use some intelligent physical switch, what I described regarding flow tables and so on, instead of being executed in the virtual space by OpenV switch, will be done directly in the fabric switch.
Okay, and there are fabric switches that can do that?
Yeah, there are a lot. It's, I would say it's almost old now, this technology.
So for the multiple virtual networks, if we're using hardware network devices, the SDN controller will configure the flow tables in which the network device so that to take into account these multiple virtual networks.
Yes.
And it sounds like then the flow tables, do they have both physical and IP address in them?
So OpenFlow is not about IPs. It's about ports on the switch. So that's how it works. So the abstraction is not done at an IP level. So the IP, the virtual IP, they never go out in the physical network. There's always some encapsulation going on, either VLAN, VXLAN, GRI, but the virtual IP, they don't go out. The way that you manage that is using the port number on the switch. So what the switch learns is that, for example, a specific packet is coming from port 1 and needs to go out of port 8, encapsulated with that technology, and the gateway is on that IP. That's what the switch knows. It doesn't know about the virtual IP.
But a lot of this is kind of almost a moot point because you don't really get to control it. It's automatically done using the software definition element or the automation of the network.
It's
you don't really have to get bogged down in it, do you? Just
no,
it goes on in the background.
No, you don't need to. Yeah, so as a user or as an admin, you don't need to dig into that. As an engineer, sometimes you do need to dig into the flows.
It's just magic.
Yeah, for you it can be magic. For me, it's sometimes it's headache. It's not magic, but yeah.
A challenge. All right.
Anything else? Okay, then thank you very much.